what would you need to know in order to, if I told you the mass, would you calculate the weight of the moon?
The effect of Earth's gravity on the moon.
Say it again?
How Earth's gravity affects the moon.
Be more specific.
The acceleration due to gravity on the moon.
Be careful about the wording. The acceleration due to the Earth's gravitation that the moon experiences. What is little g?
9.8.
No. I assume meters per second squared.
Yeah.
That would be if I'm down here, but what about if I'm way over there? It's a lot more difficult to figure out what the acceleration due to gravity is when you're dealing with outer space. Once we get beyond the surface of a planet, it becomes much more difficult. So finding weight, but matter of fact, weight of the moon doesn't really make a whole lot of sense, because weight typically is when I'm dealing with a small object right next to a large object, not when it is that kind of significant distance. So we need another way of dealing with it. There is a force due to gravity between the moon and the Earth. But calling it weight really doesn't make any sense. So if you imagine that, well, let me just throw out the thought question here. I have a universe, and in that universe I put a mass. And then I put a second mass into it. Call that M1 and M2. What's going to happen to those two masses?
They're coming together.
Okay. How does each mass know the other one exists?
Gravity.
But, all right, so it experiences gravity. What does gravity do? How does it know the gravity is there? That was an awkward question.
Each mass, I don't know. I don't even know how I would even word what's going through my head right now.
Give it a shot.
I'm guessing because each, I don't know how to say it, man. I really don't. This is the first time it's ever been like this. Like, I cannot say what's in my head.
You want to write it down?
I can't say it. That means I can't think it. Which means
Oh, okay.
it's physics, right?
All right, when you say gravity, Ethan, going back to what you had said, and Jay, just chime in if you suddenly realize how you're going to say it. You look like you're about to, but
No, because what I want to say, it don't make sense. Like,
all right, you say gravity. What do you mean by that?
The forces that would pull them. Or
All right, so in order for there to be a gravitational pull, what's wrong with the thinking of, all right, so it's not there. Suddenly, I put this mass in here and suddenly it's going to be pulled, they'll be pulled towards each other. In other words, it has to know the other one's there in order to get pulled towards it. Or maybe Coy was wrong when he said that they'll come towards each other. He's not, but the idea of why they would know why that the gravitational pull would actually attract them so that it knows that there's another mass over there is this idea that there's something that exists before the second mass shows up. If you ever see a reference to gravitational field, this has a gravitational field whether this mass is there or not.
I would never gathered the words to say that. I would never gathered the words to say that.
Well, you could hum a few bars or, get close. At some point, they made up the word gravitational field. you know, their word's not necessarily better than yours. Might be better understood in certain circles. So there's this pull here that has to do with this mass, and there's gonna be a pull there which has to do with that mass. In other words, we come up with this generic equation that first has to deal with both masses. It's commutative. In other words, if I put the two masses, I have the two masses here, if I flip the positions, I should still get the same force. Well, I have only two commutative operations, multiplication or addition. Just tell you it's multiplication. But this idea that there's this field that this is giving off something that the other mass is going to sense. So if you imagine that it's just giving off, and I'll be the only one to refer to them as this, but sort of gravitational pheromones. It's giving this something off, so just imagine it gives this burst of these pheromones out in all directions. Well, whatever burst that's being given out is going to get weaker as it gets farther out. So imagine you've got putty or glass, there we go. If you ever see glass blowers, you start out with this big blob of glass, you blow air into it, and as it stretches out, it's not like you're adding more glass to it. Just the glass gets thinner and thinner as you expand it. So this sphere of pheromones that's going out will just get thinner and thinner. And then it'll give another burst after that, and then another one and another one. But this idea that it's giving, whatever it's giving off gets weaker and weaker the farther out it gets. Just imagine I've got a sphere of these pheromones that will then expand. Not adding more pheromones in that sphere, might add a second sphere, but not adding more pheromones in that sphere. Well, the strength of them is proportional to, or inversely proportional to, the surface area. Got a certain amount that gets stretched thinner and thinner. Well, what's the surface area of a sphere? Sorry, you about to say?
Is it 4/3 pi r cubed?
That's the volume.
Okay.
So the volume, 4/3 pi r cubed. Take the derivative with respect to the radius.
Or pi r squared.
There we go. In essence, what I was, the whole lead up to this was to get to the r squared bit. That the farther you are away, the weaker the gravitational pull, and it's inversely related to the radius squared. So there's an r squared on the bottom.
Is that supposed to be like a, is that F3? Is that
That's a subscript G. This is the gravitational force. And the only thing that's missing here is we need units to match. So depending on what unit system you're using will affect this number right here. This is sort of a conversion factor, but this is a capital G. There are three things that students tend to all call the same thing called gravity. Big G, little g, and the force due to gravity. This is why I get picky about the wording on that, because they are three related but different things. This big G there is called the gravitational constant. Some textbooks, I don't think it's in many textbooks nowadays, but at one point it was called the universal gravitational constant, so I'm going to put that in parentheses just in case you happen to see universal in there. At some point, the question was, is it really universal? We're sitting here on Earth, and we were making a judgment about this constant, which is gonna be true for the entire universe. Also, since the universe doesn't behave the way we expect, one of the theories was this value of big G is actually different in different parts of the universe. Right now, the current theories are dark matter and dark energy are affecting the universe more. But at least in our corner of the universe, G is constant. There's also the possibility that big G actually changes with time, and we just don't know.
But, so, dark matter does play a part in physics too?
Yes.
That's insane.
Yeah,
I thought that was like made up.
well,
Like,
all right, so theorists make up all sorts of stuff. 99+% of the stuff that they make up is just pure crap. But some of it sort of stands the test of time and makes it into the textbooks and makes it into the news. So that's one of the ones that seems to stand the test of time. Now, one of the, we'll get into it now. Let's talk a little bit about dark matter. All right, so suppose you're in a room and you're standing on a scale and you have no idea what's outside the room. You're in this room, it's completely blocked off, you're standing on the scale, and let's make this simple math, it's a 100 kilogram person. The person looks at the scale, and the scale's reading 980 newtons. What conclusions can this person draw from this?
You can figure out their acceleration due to gravity.
Okay, that is one interpretation, that there's a planet underneath here, and the acceleration due to gravity, 9.8 meters per second squared. What's another interpretation?
Well, their weight is 980 newtons.
All I said was the scale was reading 980 newtons.
What if the box they're standing in is accelerating upward to 9.8 meters?
And that's another possibility. So if that's accelerating at 9.8 meters per second squared, and there's no planet there, the scale would read the exact same thing. There is no test that can tell the difference between these two. So, Einstein looked at these two things and said, well, there's an equivalence here. If there's no test to tell the difference between the two, then we should treat them the same. Now, in this particular situation here, if I have a laser light that's being shot across, well, if there's no acceleration, this thing is going to, the light would hit straight across here, but because the thing's getting faster and faster in that direction, the light actually would curve and hit below whatever height it initially was. If that's true there, then Einstein said, well, the same thing should happen here. There's a law in modern physics that, as one author put it, just seem like a huge guesses with no actual reasoning for why it works, but it turns out it does work. If Einstein is correct on this, then the fact that there's a planet here is warping space itself. It's causing curvature of space. The classic example is if I have a trampoline and I put a bowling ball in it, the thing warps. Now just add another dimension to it and you have closer to this. So if space is warped because of mass, so if I have some big mass right here, and I have a light source coming over here, and light's coming from it, so let's say I got a sun over here. The sun's coming along, the light's gonna hit this and then curve, and the light's gonna come along this way and it's going to curve. And so if we happen to be right here, observing it, to us it would look like this object is here and here. We would see a repeated image of it. Or at 360, if it's perfectly lined up, there'd just be this smear of light. This is known as gravitational lensing. And this was first predicted in 1915 and first seen in it's either 18 or 19, I think it was 19. This whole idea here is what's known as general relativity. Gravitational lensing was the first big piece of evidence. Now, let's connect this up to dark matter. There are pictures out there that we've taken with Hubble and whatever the next generation is, where you see this big smear of light sort of around something, but we can't see anything in the middle.
Like a black hole?
Are you talking about like an eclipse?
No, not an eclipse. It's that there's the gravitational lensing's going on. There's a star, maybe it's a black hole, but I think there are other clues that you look for a black hole about stuff, about things that are right near the horizon but not inside the black hole that do escape, and we sort of detect those. It's Hawking radiation. So we're not seeing a black hole there, evidence of a black hole there. We're just seeing nothing there, but there's something bending the light. That's the evidence for dark matter. Now, what exactly is dark matter? Now you get into the theorists and the astrophysicists debating that one. I don't think they've come upon a final conclusion on that.
So they took a picture of the light surrounding the dark object, but they didn't try to send anything to it to see.
If we tried to send something through it, I mean, our great grandkids probably be gone dead before it ever got there. These are things way far away.
Oh. They ain't tried?
I mean, the nearest star to us is what, 3.5 years away if you're traveling at the speed of light. If it's traveling at speeds that we can actually obtain, then we're talking generations will come and go before it ever got there.
Well, at least it'll get there eventually.
And we do have, the Voyager, if you've seen Star Trek the motion picture, that was Voyager 6, but we've had other Voyagers that have been sent out in our lifetime that are just still out there sending back images, a lot of it probably of nothingness, as it's traveling between the galaxies. Imagine trying to get funding for, all right, we want to send a probe that we won't know the answer to for another 600 years. I think it'd be difficult to get funding for that. But you'll make it to Congress, and you'll get the funding.
Isn't it also likely that when it gets there, it's just gonna get crushed by all the gravity in the black hole?
Or whatever it is, yeah, it's possible to.
So all that way, possibly for that. Bro.
Yep. But when you make it to Congress, we're gonna be looking for the legislation.
That's crazy, bro. That's crazy.
All right, so from this tells us that there is a gravitational force between any two masses. Let's just do a quick plug and chug. The gravitational pull between me and the camera. Well, G is a constant. It is 6.67, at least the three significant figures, times 10 to the negative 11th Newton meter squared per kilogram squared. So the gravitational pull between me and the camera is, the magnitude of that, I should say, is 6.67 times 10 to the negative 11th times my mass, which is about 100 kilograms, times the mass of the camera, which is probably about 0.01 kilograms. 10 grams, does that seem reasonable? All right, I gotta hesitate, sure. Divided by the distance between us, which I'm gonna guess is about 3.5 meters. squared. Someone be kind enough to calculate that.
Alright, so I got another question. So you saying we each have like a gravitational pull, like each of us, like towards objects?
Yep. You're being pulled in all directions.
So, like, you're really like being pulled towards that camera.
Yeah, camera's being pulled towards me. Being pulled towards each other.
If you sat still for an eternity, would you really like sit still, or would you like gradually move for something?
Well, let's get a number here and then we'll talk about that.
5.4.
Feels bizarre.
5.4
5.4,
times 10 to the negative 12.
one more time.
5.4 times 10 to the negative 12.
Units?
Newtons
Yes,
per second squared. Oh, newtons.
just newtons. It's a force. One thing, we're finding a force here, but also the kilogram squared is gonna cancel out with those 2 kilograms, and the meter squared is gonna cancel out with that meter squared, and you're left with newtons, or recognize you're finding a force, it's newtons. All right, so the gravitational pull between me and the camera there, the camera phone, is piconewtons.
Very small.
5.4 piconewtons. The gravitational pull between me and the Earth is about 980 newtons. So it is insignificant. This is one of the reasons why when we do force diagrams, we ignore these small forces here.
Hypothetically, over an eternity, would you eventually be drawn to that camera?
If we're doing it over an eternity, then we get into the fact that we would eventually, all our atoms would decay.
Can we ignore that component?
If we ignore